Hello, my name is Thomas Biazzi, and I'm a co-author on WACV paper number 407, titled Pre-Training Boosts Out-of-Domain Robustness for Pose Estimation. A common challenge in machine learning is to produce algorithms that are robust and generalizable. In pose estimation, an ultimate goal is to produce a model that can generalize well across different identities and even across multiple species. One can evaluate robustness at a variety of scales. You can evaluate robustness across different corruptions. You can evaluate robustness across different identities and also across different species, perhaps different quadrupeds or different mammals. Of course, the broader the scale, the harder the robustness challenge becomes. In our paper, we chose to focus in on, at first, robustness across different identities. To accomplish this, we put forth a new animal pose benchmark called Horse 10. Horse 10 consists of videos of horses walking broadside from left to right. One example video can be seen here. We split up Horse 10 into two different sets. 10 horses are set aside as within-domain data. The other 20 horses are set aside as out-of-domain data. One can train a model on the within-domain horses and evaluate how that model performs on the out-of-domain horses that were not seen during training. This is a good test of out-of-domain robustness for a couple of reasons. First off, it is a low data regime. There are very few horses and very few images of those horses to train on. In addition, it directly reflects what people deal with in the real world. Many scientists train models on just a few videos of a few individuals and want those same models to generalize well to other individuals that were not seen during training. This benchmark directly reflects that task. For our paper, we focused in on a few different techniques that can be used to improve robustness on Horse 10. We first evaluated the importance of model architecture. Using Deep Lab Cut, a common pose estimation algorithm available online, we incorporated different model backbones into the convolutional architecture. Our core finding is that if you use model backbones that perform better on ImageNet, not only will you perform better on within-domain data for Horse 10, you'll perform much better on out-of-domain data for Horse 10. In addition to evaluating model architecture, we evaluated the importance of pre-training on ImageNet. Here, it was clear that pre-training on ImageNet is crucial for out-of-domain performance. The solid gray line here is the performance of a model trained from scratch. Clearly, the model trained from scratch performs nowhere near as well as the model that was pre-trained on ImageNet on out-of-domain data. For comparison to Horse 10, we also put forth Horse C. In Horse C, we augment our horse data by applying 15 common image corruptions. Now, not only could we evaluate performance across different individuals, but we could also evaluate robustness across common image corruptions. Our results on Horse C directly reflect our results on Horse 10. For one, it's clear that pre-training is crucial for out-of-domain robustness, and if your model is pre-trained, you will perform better if you use better model backbones. In addition to Horse C, we wanted to evaluate our findings on animal pose, which is a dataset that consists of 5 different species of animals. We trained our models on a single species and then evaluated how those same models performed on the other species that were not seen during training. Here, it was clear that once again, if you use model backbones that perform better on ImageNet, you'll get better performance on unseen data. In conclusion, we developed a novel pose estimation benchmark, Horse 10 and Horse C, which can be available at horse10.deeplabcut.org. Horse 10 can also be found on paperswithcode.com. In addition, we report 2 key findings which we found across all of our datasets. For one, pre-trained ImageNet networks are crucial for out-of-domain robustness. In addition, networks that have higher ImageNet performance lead to better generalization, and this is only true if you pre-train our networks. For our complete results, please refer to WACV paper number 407. Thank you for listening and have a great day.